All right, curvature is a property of a trajectory that literally measures how fast the curve is bending. If you think about two different curves here, this curve bends slowly, well, this curve bends very quickly. Right? So to quantify this, what I'm going to ask you to do is to think about how the unit tangent vector actually changes as the curve bends. If I were to take a specific spot on the curve, and let me just go right here at the top, and sketch the unit tangent vector, it would look something like that. Now I'd like to go over a little distance on the curve, maybe over to here, and sketch the unit tangent vector again. It would look something like that. I'm going to do the same thing over here. Let's go ahead and right at the peak there, the maximum, let's sketch our unit tangent vector. It would be horizontal. And then I'm going to attempt, estimating is fine, but I'm going to attempt to move about the same distance along the curve. So about that far, just kind of eyeballing it, would bring me to maybe around there or so. That little section is about the same length as that little section of the curve. And go ahead and sketch in the unit tangent vector again. Let's see, the unit tangent vector would look something like that. What I'm asking you to notice is that when I have a very slowly curving function, what we're going to call a small curvature, when I move a little distance along the curve, the unit tangent vector changes only a little bit, right? This vector and that vector aren't all that different. As opposed to here, where I have a large curvature, notice how if I moved about the same distance along the curve, my unit tangent vector now has changed a lot. It's a very different vector. So it seems as though the rate at which the unit tangent vector is changing is going to help me define the curvature. For curvature, we use the Greek letter kappa. This looks like a slightly curvy K. And if it makes sense then, it's the rate of change of the unit tangent vector that's going to define this. Rate of change is a derivative. So this would be the derivative of t. But with respect to what? It was with respect to the distance that I moved along that curve, what we usually call s, right? The distance along the curve, the arc length. And I'd like my curvature to be a scalar, not a vector. So I'm going to go ahead and take the magnitude of this. And this will be relatively small for this graph. And if I do the exact same thing, it will be relatively large for that graph. So that seems like a reasonable definition of curvature, how fast the unit tangent vector is changing with respect to distance or arc length along the curve. And while it makes sense, the problem is it's not real easy to calculate. Remember, most of the time when we've got a curve R, we don't have it parameterized with respect to S. We usually have it parameterized with respect to t. So getting these derivatives is not going to be easy because I don't usually have R of S. I usually have R of t. So for that reason, I need some alternative formulas. And I'm actually not going to be taking the time to verify these for you. It is done and derived in your book, so I would encourage you to look at that. But I'm going to tell you that this value for kappa can also be calculated in two other ways. I can take the derivative of the unit tangent with respect to t. Notice that's better. I usually have things in terms of t, divided by the magnitude of dr dt. Or I can also use the formula velocity cross acceleration, magnitude, divided by the magnitude of the velocity cubed. For most people, this one is going to be my preferred method. We're so used to calculating velocities and accelerations that it's pretty quick, and then we can just throw it into that formula. So when I'm asked to find a curvature, I'll generally go about it that way. All right, let's give this a shot. In example 2, I'd like to find an expression for the curvature of r of t, which is 2 cosine ti plus 2 sine tj. As we just saw, there's a convenient formula if I can write down the v and the a formulas. So in this case, my velocity, r prime, would be negative 2 sine t I plus 2 cosine t j. My acceleration, r double prime, will be negative 2 cosine t I plus negative 2 sine t j. In order to use my curvature formula, I'm going to need the cross product for v and a. So let's do v cross a. Now I do have to have a three-dimensional cross product, so I'll put zeros in for the k's. And notice that even though I have functions instead of just numbers, I can still do my cross product. However you're doing your cross product, same method's still going to apply. So in my case, I'm going to get 0 for I, 0 for j, and a positive 4 sine squared t for k. Subtract. This one will give me a negative 4 cos squared t for k. And 0 for I, 0 for j. So I actually have 4 sine squared plus 4 cos squared, which is just 4 for k. So in this case, the cross product, v cross a, is just a constant vector, 4k. And now I'm ready to go ahead and haul out my curvature formula. From the previous page, curvature is the magnitude of v cross a divided by the magnitude of v cubed. So let's see. V cross a was 4k, or 004. So technically its magnitude is the square root of 0 squared plus 0 squared plus 4 squared. Of course, this is just 4 units up the z-axis, so you really already knew the magnitude was 4 anyway. And on the bottom, I want the magnitude of v. So that would be the square root of, that'll be a 4 sine squared t plus 4 cos squared t. And that's going to get cubed. All right, so the numerator, square root of 16 is 4. And in the denominator, 4 sine squared plus 4 cos squared, of course, is really just 4 under that radical. So that would be 2 cubed, or 8, giving me a curvature of 1/2. Now, curvature won't always be constant. There's certainly plenty of curves that have different amounts of bend at different parts of them. But this one turned out to be a constant. And it makes sense if you think about the original curve, right? What was this? That's just a circle of radius 2. So if I sketched myself a little graph of r of t, it's just a circle of radius 2. And indeed, it doesn't really matter where you look on this curve. It bends the same amount all the time. That amount of bend we're now defining as the curvature, 1/2. By the way, we did have a radius of 2 on our circle. And notice the reciprocal relationship here between the curvature and the radius. That's not an accident. In general, the curvature of a circle will always be the reciprocal of its radius. If you think about it, if I had a much larger circle, maybe a radius of 5 or something, this circle doesn't bend as quickly because it doesn't have to get around as fast, right? So if this radius was 5, its curvature would actually be the reciprocal 1/5. It would have a smaller curvature because it bends more slowly than that one. All right, one more example. I'd like to find an expression for the curvature of the function 3t, t squared, t. I've actually got a maple graph of that curve down at the bottom of the page for you. And we'll go ahead and find the expression for the curvature, and then we'll calculate the curvature at several different points and fill in the table at the bottom of the page. So, once again, I have a nice convenient curvature formula in terms of velocity and acceleration. So my velocity vector, the first derivative, would be 3, 2t, 1. And my acceleration vector, second derivative, 0, 2, 0. Curvature formula requires the cross product. This one's already three-dimensional. So 0 for I, 0 for j, 6k, minus 0 for k, 2i, and 0 for j. So it looks like we have a constant cross product of -2, 0, 6. All right, curvature, magnitude of v cross a over the magnitude of v cubed. Magnitude of our v cross a would be the square root of 4 plus 0 plus 36. And then the magnitude of v would be the square root of 9 plus 4t squared plus 1, and that's supposed to be cubed. So I have the square root of 40 over the square root of 4t squared plus 10 to the third power. I mean, we could simplify that a little if we wanted to, but we're just going to plug numbers into it in a minute anyway, so no real need to. All right, couple things. Let's take a look at that formula for a moment and think about what makes that larger or smaller. The only variable is in the denominator. So, if t is 0, this is as big as it's ever going to get. As t moves further away from 0, in either the positive or the negative direction, the denominator is going to keep getting bigger and bigger, meaning my curvature is going to get smaller. I think that's going to make sense when you look at the picture. Right? The vertex of this parabola is right at 0, 0, and that's where the curve is bending fastest. If you move in either direction out away from the vertex, the rate at which the curve bends gets much less. So I'm expecting, and I'm only going to go out in the positive direction, I'm expecting my curvature to be as large as it'll ever be at 0, and for the curvature to get smaller and smaller as we move away from 0. Let's go ahead and do that. And I'm just going to rewrite this right here, square root of 40, and I'm going to make that 4t squared plus 10 to the 3/2. And I'm actually just going to put that in my calculator so I don't have to keep typing it in. Oops, I've got parametric mode going. So there's my function. And we wanted to know what the curvature was at 0, 1, 2, and 3. Oops, I lost my 0. Put that back in. So at 0, we get 0.2. At 1, I've got about 0.12. 2 is about 0.05. I'm just keeping 2 decimal places here. And 3 is about 0.02. So first of all, you can definitely see that what we predicted is true. The further away from the vertex, the further away from the point here at t equals 0, the less this curve bends. In fact, by the time we get out to t equals 3, this isn't too far off of a straight line, right? A straight line would have 0 curvature, and this has got only a very, very small curvature. Well, it's true with a parabola, right? Once you get out far enough, the curve is very, very slight. All right, the radius of curvature, we're just going to take a lesson here from what we saw with the circle. The radius of curvature is actually the reciprocal of the curvature. So if you just take 1 over these values, 1 over 0.2 would be 5. 1 over 0.12 is about 8.33. 1 over 0.05, that'd be 20. And 1 over 0.02, that would be 50. Here's what the radius of curvature actually tells us when we've got a curve that's not a circle. It tells us the radius of the tangent circle. If I imagine right at t equals 0, which would be the origin, a circle that just touches the graph at that point, that circle would have a radius of 5. That's what the radius of curvature actually tells us. The radius of the tangent, or we sometimes call it the osculating circle. And notice those osculating circles would grow bigger and bigger and bigger as we came out further on our graph. All right, so that's curvature. We will come back for one last video in this section on components of acceleration.